Hello everyone, welcome back. Today we're going to learn the quadratic functions and equations.
Quadratic functions and equations 3000.
The first section for this lesson is intro to this thing.
Parabolas.
Parabolas. Alright.
In this video, we're going to talk about one of the most common types of curves you will see in mathematics, and that is the parabola. And the word parabola sounds quite fancy, but we'll see it's describing something that is fairly straightforward. Now, in terms of why it is called the parabola, I've seen multiple explanations for it. It comes from Greek, para, that root word, similar to parable. You could view of something beside, alongside, something in parallel. Bola, same root as when we're talking about ballistics, throwing something. So you could interpret it as beside, alongside, something that is being thrown. Now, how does that relate to curves like this? Well, my brain immediately imagines, well, this is the trajectory. This is the path that is a pretty good approximation for the path of things that are actually thrown. And when you study physics, you will see the path, you will approximate the paths of objects being thrown as parabolas. So maybe that's where it comes from. But there are other potential explanations for why it is actually called the parabola. It has been lost to history. But what exactly is a parabola? In future videos, we're going to describe it a little bit more algebraically. In this one, we just want to get a sense for what parabolas look like and introduce ourselves to some terminology around a parabola. So these three curves, they are all hand-drawn versions of a parabola. And so you immediately notice some interesting things about them. Some of them are open upwards, like this yellow one and this pink one, and some of them are open downwards. And you will hear people say things like open down, open downwards, or open down, or open upwards. So it's good to know what they're talking about. And it's hopefully fairly self-explanatory. Open upwards, the parabola is open towards the top of our graph paper. Here it's open towards the bottom of our graph paper. This looks like a right side up U. This looks like an upside down U right over here. This pink one would be open upwards. Now, another term that you'll see associated with a parabola, and once again in the future we'll learn how to calculate these things and find them precisely, is the vertex. And the vertex you should view as the maximum or minimum point on a parabola. So if a parabola opens upwards, like these two on the right, the vertex is the minimum point. The vertex is the minimum point right over there. And so if someone said, what is the vertex of this yellow parabola? Well, it looks like the x coordinate is 3.5. So it is 3.5. And it looks like the y coordinate, it looks like it is about -3.5. And once again, once we start representing these things with equations, we'll have techniques for calculating them more precisely. But the vertex of this other upward opening parabola, it is the minimum point. It is the low point. There is no maximum point on an upward opening parabola. It just keeps increasing as x gets larger in the positive or the negative direction. Now, if your parabola opens downward, then your vertex is going to be your maximum point. Now, related to the idea of a vertex is the idea of an axis of symmetry. And in general, when we're talking about, well, not just two dimensions, but even 3 dimensions, but especially in 2 dimensions, you can imagine a line over which you can flip the graph, and so it folds on to itself. And so the axis of symmetry for this yellow graph right over here, for this yellow parabola, it would be this line. I actually draw it a little bit better. It would be that line right over there. You could fold the parabola over that line and it would meet itself. And that line, I didn't draw it as neat as I should, that should go directly through the vertex. So to describe that line, you would say that line is x is equal to 3.5. Similarly, the axis of symmetry for this pink parabola, it should go through the line x equals -1. So let me do that. That's the axis of symmetry. It goes through the vertex. Do that. That's the...
Okay, wait a minute. For now, we just learned a new word, the axis of symmetry. What's that mean? That means if you have a graph, or if you have a graph like this, okay, what's the axis of symmetry? If you imagine it as a circle, the axis of symmetry is just inside between the object, which is this one. Okay, it's right in the center. It split the whole object into two equal parts.
Axis of symmetry. It goes through the vertex. And if you were to fold the parabola over it, it would meet itself. The axis of symmetry for this green one, it should once again go through the vertex. It looks like it is x is equal to -6. This is, let me write that down, that is the axis of symmetry. Now, another concept that isn't unique to parabolas, but we'll talk a lot about it in the context of parabolas, are intercepts. So when people say y-intercept, and you saw this when you first graphed lines, they're saying where does the curve intercept or intersect the y-axis? So the y-intercept of this yellow line would be right there. It looks like it's the point 0, 3. 0, 3. The y-intercept for the pink one is right over there. We, at least on this graph paper, we don't see the y-intercept, but it eventually will intersect the y-axis. It just will be way off of this screen. Now, you might also be familiar with the term x-intercept, and that's especially interesting with parabolas, as we'll see in the future. X-intercept is where you intercept or intersect the x-axis. And here, this yellow one, you see it does it 2 places. And this is where it gets interesting. Lines will only intersect the x-axis once, but at most. But here, we see that a parabola can intersect the x-axis twice because it curves back around to intersect it again. And so for here, the x-intercepts are going to be the point 1, 0 and 6, 0. Now you might already notice something interesting. The x-intercepts are symmetric around the axis of symmetry. So they should be equidistant from that axis of symmetry. And you can see they indeed are. They're both exactly 2.5 away from that axis of symmetry. And so if you know where the intercepts are, you just take, you could say, the midpoint of the x-coordinates, and then you're going to have the axis of symmetry, the x-coordinate of the axis of symmetry, and the x-coordinate of the actual vertex. Similarly, the x-intercepts here looks like it's negative, the points are -7, 0 and -5, 0. And the x-coordinate of the vertex, or the line of symmetry, is right in between those 2 points. Now, it's worth noting, not every parabola is going to intersect the x-axis. Notice this pink upward opening parabola, its low point is above the x-axis. So it's never going to intersect the actual x-axis. So this is actually not going to have any x-intercepts.
Alright, enough talking, but through this video, we have at least know one thing. Yeah, when it comes to the maximum point or the minimal point of the parabola, yeah, that's how they call it. They call this graph or this graph parabola. Yeah, for the minimal points or the maximum point, what do they call it? They call it a vertex. They call it that. That makes sense because at other scenarios, people also love to call that point a vertex instead of the maximum or minimum point. If you know this, you would be better to understand those different terms which refers to the same thing.
Katie throws a ball in the air for her dog to chase. The function f models the height of the ball in meters as a function of time in seconds after Katie threw it. And we could see that right over here. This is our function f. So at time t equals 0, the height looks like it's a couple of meters. And then as we go forward in time to a little under 2.5 seconds, the ball is going up. And then after a little under 2.5 seconds, the ball starts going down. And after, by the time you get to 5 seconds or close to 5 seconds, it looks like the ball is on the ground. Its height is 0 meters. So then they ask us, which of these statements are true? Choose all that apply. So pause this video and see if you can work it out. All right, now let's look through the choices. So the first one says, Katie threw the ball from a height of 5 meters. So let's see if that bears fruit, or see if that's true. So if she threw it from a height of 5 meters, that means that the y-intercept would have been at 5 meters. At time t equals 0, it would have been at a height of 5 meters. Clearly, that is not the y-intercept. It looks like she threw it from a height of maybe 1.5 or 2 meters. So I'm assuming that Katie is not 5 meters tall, so she wasn't on a ladder or anything. She just threw it from her regular height. And so we can rule out this first choice. The second one says, at its highest point, the ball was about 31 meters above the ground. Let's see if that is true. So the highest point is right over here. And yeah, that looks about 31 meters. So I like that choice. So I will select that one. The ball was in the air for about 2.5 seconds. So we can clearly see that that is not the case. The ball was going up for about 2.5 seconds, but then it was going down for roughly another 2.5 seconds. And so it was actually in the air for almost 5 seconds. So I would rule this one out. The ball reached its highest point in the air about 2.5 seconds after Katie threw it. So let's see. After Katie, 2.5 seconds after Katie threw the ball, it's right over there. It looks like it reached its highest point a little bit before that, but they said about, so they're speaking in rough terms. So I think that statement can be true. It's about 2.5 seconds. If they said exactly 2.5 seconds, I wouldn't have selected it because it seems like it happened at like 2.45 seconds or something like that. But there you go. Those are the ones that seem true.
Solving and graphing with factored form. What does that mean?
Let's say that we've got the equation 2x minus 1 times x plus 4 is equal to 0. Pause this video and see if you can figure out the x values that would satisfy this equation, or essentially our solutions to this equation. All right, now let's work through this together. So at first, you might be tempted to multiply these things out, or there's multiple ways that you might have tried to approach it. But the key realization here is that you have two things being multiplied, and it's being equal to 0. So you have the first thing being multiplied is 2x minus 1. This expression is being multiplied by x plus 4. And to get it to be equal to 0, one or both of these expressions needs to be equal to 0. Let me really reinforce that idea. If I had two variables, let's say a and b, and I told you a times b is equal to 0. Well, can you get the product of two numbers to equal 0 without at least one of them being equal to 0? And the simple answer is no. If a is 7, the only way that you would get 0 is if b is 0. Or if b was 5, the only way to get 0 is if a is 0. So you see from this example, either, let me write this down, either a or b or both, because 0 times 0 is 0, or both must be 0. The only way that you get the product of two quantities and you get 0 is if one or both of them is equal to 0. I really want to reinforce this idea. I'm going to put a red box around it so that it really gets stuck in your brain. And I want you to think about why that is. Try to come up with two numbers. Try to multiply them so that you get 0, and you're going to see that one of those numbers is going to need to be 0. So we're going to use this idea right over here. Now this might look a little bit different, but you could view 2x minus 1 as our a, and you could view x plus 4 as our b. So either 2x minus 1 needs to be equal to 0, or x plus 4 needs to be equal to 0, or both of them needs to be equal to 0. So I could write that as 2x minus 1 needs to be equal to 0, or x plus 4, or x, let me do that orange. Actually, let me do the 2x minus 1 in that yellow color. So either 2x minus 1 is equal to 0, or x plus 4 is equal to 0. X plus 4 is equal to 0. And so let's solve each of these. If 2x minus 1 could be equal to 0, well, let's see, we could add 1 to both sides, and we get 2x is equal to 1. Divide both sides by 2. And this is just straightforward solving a linear equation. If this looks unfamiliar, I encourage you to watch videos on solving linear equations on Khan Academy. But you'll get x is equal to 1/2 as one solution. And this is interesting because we're going to have two solutions here. Or over here, if we want to solve for x, we can subtract 4 from both sides. And we would get x is equal to -4. So it's neat. In an equation like this, you can actually have two solutions. X could be equal to 1/2, or x could be equal to -4. And I think it's pretty interesting to substitute either one of these in. If x is equal to 1/2, what is going to happen? Well, this is going to be 2 times 1/2 minus 1, 2 times 1/2 minus 1. That's going to be our...
We just learned about another sentence, which is to substitute one into another. It means use the first one to replace the another one. So this sentence, let me repeat it again. To substitute this one into this expression.
To substitute either one of these in. If x is equal to 1/2, what is going to happen? Well, this is going to be 2 times 1/2 minus 1, 2 times 1/2 minus 1. That's going to be our first expression. And then our second expression is going to be 1/2 plus 4. And so what's this going to be equal to? Well, 2 times 1/2 is 1. 1 minus 1 is 0. So I don't care what you have over here. 0 times anything is going to be equal to 0. So when x equals 1/2, the first thing becomes 0, making the product equal 0. And likewise, if x equals -4, it's pretty clear that this second expression is going to be 0. And even though this first expression isn't going to be 0 in that case, anything times 0 is going to be 0. Let's do one more example here. Let me delete out everything that I just wrote here. And so I'm going to involve a function. So let's say someone told you that f of x is equal to x minus 5 times 5x plus 2. And someone said, find the zeros of f of x. Well, the zeros are, what are the x values that make f of x equal to 0? When does f of x equal 0? For what x values does f of x equal 0? That's what people are really asking when they say, find the zeros of f of x. So to do that, well, when does f of x equal 0? Well, f of x is equal to 0 when this expression right over here is equal to 0. And so it sets up just like the equation we just saw. X minus 5 times 5x plus 2, when does that equal 0? And like we saw before, this is just like what we saw before, and I encourage you to pause the video and try to work it out on your own.
Okay, I'll just work it out by my own. So for this one, if this expression is true, then there has probably 3 possibilities. The first one is x minus 5 equal to 0. If this one is true, we can get that x probably is equal to 5. And the second possibility is 5x plus 2 equal to 0. And for this condition, that would be, let's say, -2 divided by 5. This is x. Alright. And let me say, okay, I guess this is the solution. 5 or -2 over 5. Ta-da!
So,
I am right, as you could say. We got the right answer here.
here are two zeros. You input either one of these into f of x. If you input x equals 5, if you take f of 5, if you try to evaluate f of 5,
Solving by taking the square root. What is that?
We're asked to solve the equation 2x squared plus 3 is equal to 75. So in this situation, it looks like we might be able to isolate the x squared pretty simply because there's only one term that involves an x here. It's only this x squared term. So let's try to do that. So let me just rewrite it. We have 2x squared plus 3 is equal to 75. I'm going to try to isolate this x squared over here. The best way to do that, or at least the first step, would be to subtract 3 from both sides of this equation. So let's subtract 3 from both sides. The left-hand side, we're just left with 2x squared. That was the whole point of subtracting 3 from both sides. And on the right-hand side, 75 minus 3 is 72. Now I want to isolate this x squared. I have a 2x squared here. So I could have just an x squared here if I divide this side, or really both sides, by 2. Anything I do to one side, I have to do to the other side if I want to maintain the equality. So the left side just becomes x squared, and the right-hand side is 72 divided by 2 is 36. So we're left with x squared is equal to 36. And then to solve for x, we can take the plus or minus square root of both sides. So we could say the plus, or let me write it this way. If we take the square root of both sides, we would get x is equal to the plus or minus square root of 36, which is equal to plus or minus 6. Let me just write that on another line. So x is equal to plus or minus 6. And remember here, if something squared is equal to 36, that something could be the negative version or the positive version. It could be the principal root or it could be the negative root. Both negative 6 squared is 36 and positive 6 squared is 36. So both of these work. And you could put them back into the original equation to verify it. Let's do that. If you say 2 times 6 squared plus 3, that's 2 times 36, which is 72, plus 3 is 75. So that works. If you put negative 6 in there, you're going to get the exact same result because negative 6 squared is also 36. 2 times 36 is 72, plus 3 is 75.
Okay. I didn't learn anything from that video because we already know that, right?
Vertex form.
Vertex form. You know what? I start to think about those lessons. I start to think that maybe the Chinese mathematics lessons are just a copy from the English mathematics system. So, if you are a student, you'd better just get started to learn the English version instead of the Chinese version because between the copy process, there might drop some knowledge or information. So that's bad for you guys, right? If you miss some piece of that knowledge, then you cannot just link those things together to get a whole picture, right?
it might not be obvious when you look at these three equations, but they're the exact same equation. They've just been algebraically manipulated. They are in different forms. This is the equation in sometimes called standard form for a quadratic. This is the quadratic in factored form. Notice this has been factored right over here. And this last form is what we're going to focus on in this video. This is sometimes known as vertex form. And we're not going to focus on how do you get from one of these other forms to vertex form in this video. We'll do that in future videos. But what we're going to do is appreciate why this is called vertex form. Now to start, let's just remind ourselves what a vertex is. So as you might remember from other videos, if we have a quadratic, if we're graphing y is equal to some quadratic expression in terms of x, the graph of that will be a parabola. And it might be an upward opening parabola or a downward opening parabola. So this one in particular is going to be an upward opening parabola. And so it might look something like this. So it might look something like this right over here. And for an upward opening parabola like this, the vertex is this point right over here. You could view it as this minimum point. You have your x-coordinate of the vertex right over there, and you have your y-coordinate of the vertex right over here. Now, the reason why this is called vertex form is it's fairly straightforward to pick out the coordinates of this vertex from this form. How do we do that? Well, to do that, we just have to appreciate the structure that's in this expression. Let me just rewrite it again. We have y is equal to 3 times x plus 2 squared minus 27. The important thing to realize is that this part of the expression is never going to be negative. No matter what you have here, if you square it, you're never going to get a negative value. And so if this is never going to be negative, and we're multiplying it by a positive right over here, this whole thing right over here is going to be greater than or equal to 0. So another way to think about it, it's only going to be additive to negative 27. So your minimum point for this curve right over here, for your parabola, is going to happen when this expression is equal to 0, when you're not adding anything to negative 27. And so when will this equal 0? Well, it's going to be equal to 0 when x plus 2 is going to be equal to 0. So you could just say, if you want to find the x-coordinate of the vertex, well, for what x value does x plus 2 equal 0? And of course, we can subtract 2 from both sides, and you get x is equal to negative 2. So we know that this x-coordinate right over here is negative 2. And then what's the y-coordinate of the vertex? You could say, hey, what is the minimum y that this curve takes on? Well, when x is equal to negative 2, this whole thing is 0, and y is equal to negative 27. Y is equal to negative 27. So this right over here is negative 27. And so the coordinates of the vertex here are negative 2, comma, negative 27. And you were able to pick that out just by looking at the quadratic in vertex form. Now let's get a few more examples under our belt so that we can really get good at picking out the vertex when a quadratic is written in vertex form. So let's pick a scenario where we have a downward opening parabola, where y is equal to, let's just say, negative 2 times x plus 5. Actually, let me make it x minus 5. X minus 5 squared, and then let's say plus 10. Well, here, this is going to be downward opening, and let's appreciate why that is. So here, this part is still always going to be non-negative, but it's being multiplied by a negative 2. So it's actually always going to be non-positive. So this whole thing right over here is going to be less than or equal to 0 for all x's. So it can only take away from the 10. So where do we hit a maximum point? Well, we hit a maximum point when x minus 5 is equal to 0, when we're not taking anything away from the 10. And so x minus 5 is equal to 0. Well, that, of course, is going to happen when x is equal to 5. And that, indeed, is the x-coordinate for the vertex. And what's the y-coordinate for the vertex? Well, if x is equal to 5, this thing is 0. You're not going to be taking anything away from the 10, and so y is going to be equal to 10. And so the vertex here is x equals 5, which, and I'm just going to eyeball it. Maybe it's right over here. X equals 5. And y is equal to 10. If this is negative 27, this would be positive 27. 10 would be something like this. Not using the same scales for the x and y axis, but there you have it. So it's 5, comma 10. And our curve is going to look something like this. I don't know exactly where it intersects the x-axis, but it's going to be a downward opening parabola. Let's do one more example, just so that we...
I don't want to do more examples because I think I already done enough drawing back in my, not high school, but below that.
Solving quadratics by factoring.
Solving quadratics by factoring. Yeah, let me solve that. Or let us solve that.
We're asked to solve for s, and we have s squared minus 2s minus 35 is equal to 0. Now, if this is the first time that you've seen this type of what's essentially a quadratic equation, you might be tempted to try to solve for s using traditional algebraic means. But the best way to solve this, especially when it's explicitly equal to 0, is to factor the left-hand side and then think about the fact that those binomials that you factor into, that they have to be equal to 0. So let's just do that. So how can we factor this? We've seen it several ways. I'll show you kind of the standard way we've been doing it by grouping. And then there's a little bit of a shortcut when you have a 1 as a coefficient over here. So when you look at something, when you do something by grouping, when you factor by grouping, you think about two numbers whose sum is going to be equal to -2. So you think about two numbers whose sum, a plus b, is equal to -2, and whose product is going to be equal to -35. A times b is equal to -35.
Alright, guys, think about this formula. You know, back in school, my teacher and the whole system never ever told me that I could solve this equation with this simple formula. So let me just do it by myself and see if I can make it right. For example, now we already have this this two expressions or equations. How can we solve it? Alright, let me do it this way. For the first expression or equation, we could get a is equal to -2 minus b, right? And then we substitute this expression into the second equation, right? So that would be -2 minus b times b equal to -35. Then we distribute this expression into this form. -2b minus b squared equal to -35. For this one, do you know what I was thinking about? I was thinking that this exactly, let me say, like the old one that we have, or not. Let me do this. Okay, in the end, this is what we got. Did you think that those two equations are similar? Okay, if that's true, I'm gonna use the first equation to minus the second equation. So we would treat this b as the s. So the s squared canceled out. -2s minus the 2b would be equal to 4s. Then -35 minus -35 would be equal to 0. So in the end, we got something like this, 4s equal to 0. And clearly that's not right. Okay, I'll just say how they do it.
Since the product is a negative number, one has to be positive, one has to be negative. And so if you think about it, ones that are about 2 apart, you have 5 and -7. I think that'll work. 5 plus -7 is equal to -2. So to factor by grouping, you split this middle term into we can split this into let me write it this way. We have s squared, and then this middle term right here, I'll do it in pink. This middle term right there, I can write it as plus 5s minus 7s, and then we have the minus 35. And of course, all of that is equal to 0. Now, we call it factoring by grouping because we group it. So we can group these first two terms. And these first two terms, they have a...
All right, it seems like that Cohen himself didn't even try to solve this problem. He just immediately get that answer. But that may not be able to apply to us. So we need to solve it, right? Okay, so let me do this again. For this time, we'll do it in a different way. For example, we could say a is equal to -35 divided by b. We put that stuff into the first equation. Then it's equal to -2. We think about this. We can make the negative sign cancel out. How can we do that? We every term in this equation by -1. So in the end, we will get something like this. 35 over b minus b equal to 2. Then we could even do more. For example, we could say, we could times each term by b. So in the end, we will get something like this. 35 minus 35b. Oh, sorry, that's not the case. Minus b squared minus 2b equal to 0. Yeah, for this one, we still couldn't solve it unless we... Oh, Yeah, for this time, that would be probably different. Let me say, if we add this equation to this equation, we add them together, what we would get? We'll get negative 4s equal to 0, which is again is wrong. So I was thinking about this. Where's the problem? Can I really solve this problem? Now I'm gonna do it again. For example, a equal to negative 2 minus b, right? This is absolutely true. Then I'm gonna say negative 2 minus b times b equal to negative 35. Then, let me think about this. What kind of value that would cause this result? What if the b equal to negative 7? Minus negative 7 would be equal to 7. 7 minus 2, that would be 5. 5 times negative 7 would be negative 35. Yeah, that's correct. But the problem is, how do you know that the b is the negative 7 at the first place? The problem is you do not know that. Of course, we could use Python or any programming language to solve this equation for us. But let's say with our pure hands or with our own brain, how can we do that? Okay, let me do it again. Negative b squared minus 2b plus 35 equal to 0. For this one, negative 1, or that's not right. Say a plus b equal to negative 2. And a times b equal to negative 35. So what I just found? I found if we want to solve this equation, we'll have to do the same thing again, which is a loop, which will never get us to the right answer. So this method will never work. You'll never be able to find the solution by using the two equations right in here. You'll get a loop.
Common factor of s. So let's factor that out. You have s times s plus 5. That's the same thing as s squared plus 5s. Now in these second two terms right here, you have a common factor of negative 7. So let's factor that out. So you have negative 7 times s plus 5. And of course, all of that is equal to 0. Now we have two terms here where both of them have s plus 5 as a factor. Both of them have this s plus 5 as a factor. So we can factor that out. So let's do that. So you have s plus 5 times this s times this s right here, right? S plus 5 times s would give you this term. And then you have minus that 7 right there. Minus that 7. I undistributed the s plus 5. And then this is going to be equal to 0. Now that we've factored it, we just have to think a little bit about what happens when you take the product of two numbers. I mean, s plus 5 is a number. S minus 7 is another number. And we're saying that the product of those two numbers is equal to 0. If I were told you that I had two numbers, if I told you that I had the numbers a times b and that they equal to 0, what do we know about either a or b or both of them? Well, at least one of them has to be equal to 0, or both of them have to be equal to 0. So the fact that this number times that number is equal to 0 tells us that either s plus 5 is equal to 0, or, and maybe both of them, or s minus 7 is equal to 0. Or, I'll do that in just green, or s minus 7 is equal to 0. This, where you have 1 as the leading coefficient, you don't have to do this two-step factoring. Let me just show you an example. If I just have x plus a times x plus b, what does that equal to? X times x is x squared. X times b is bx. A times x is plus ax. A times b is ab plus ab. So you get x squared plus, these two can be added, plus a plus bx plus AB. And that's the pattern that we have right here. We have 1 as a leading coefficient here. We have 1 as a leading coefficient here. So once we have our two numbers that add up to -2, so once we have our two numbers that add up to -2, that's our a plus b, and we have our product that gets to -35, then we can straight just factor it into the product of those two things. So it'll be, or the product of the binomials where those will be the a's and the b's. So it'll be, so we figured out it's 5 and -7. 5 plus -7 is -2. 5 times -7 is
Okay, so now
-35.
So now I understand how they did that. Basically, they are doing it by guessing. You know, they try to come up with two numbers in their mind that add up together equal to the middle number here. For example, for this particular case, that would be a plus b equal to -2. They come up with two numbers in their mind that equal to this number. For example, 5 minus 7. And just happened that 5 times -7 also equal to the last number that they have. For example, in this particular case is -35. So that was let me say stupid. They do the whole stuff by guessing. You know, there has no particular rules for calculating such values. For example, the a and b. So I guess that's probably not the best way for doing the mathematics. You cannot always do the calculation by guessing. That's not accurate. There must have some special way or method to do it right, to do it logically or precisely.
So we could have just straight factored at this point 2, well actually this was the case of s, so we could have factored it straight to the case of s plus 5 times s minus 7. We could have done that straight away, and we've gotten to that right there. And of course, that whole thing was equal to 0. So that would have been a little bit of a shortcut, but factoring by grouping will it's a completely appropriate way to do it as well.
So we have 6x squared minus 120x plus 600 equals 0. Like always, pause this video and see if you can solve for x, if you can find the x values that satisfy this equation. All right, let's work through this together. So the numbers here don't seem like outlandish numbers. They seem like something that I might be able to deal with and I might be able to factor. So let's try to do that. So the first thing I like to do is see if I can get a coefficient of 1 on the second degree term, on the x squared term. And it looks like actually all of these terms are divisible by 6. So if we divide both sides of this equation by 6, I'm still going to have nice integer coefficients. So let's do that. Let's divide both sides by 6. So if we divide the left side by 6, divide by 6, divide by 6, divide by 6, and I divide the right side by 6. So if I do that, and clearly if I do the same thing to both sides of the equation, then the equality still holds. On the left-hand side, I am going to be left with x squared, and then negative 120 divided by 6. That is, let's see, 120 divided by 6 is 20. So that's minus 20x. And then 600 divided by 6 is 100. So plus 100 is equal to 0 divided by 6 is equal to 0. So let's see if we can factor, if we can express this quadratic as a product of two expressions. And the way we think about this, and we've done it multiple times, if we have x plus a times x plus b, and this is hopefully a review for you. If you multiply that out, that is going to be equal to, that equals to x squared plus a plus b x plus ab. And so what we want to do is see if we can factor this into an x plus a and an x plus b. And so a plus b needs to be equal to negative 20. That needs to be a plus b. And then a times b, right over here, that needs to be equal to the constant term. That needs to be a times b right over there. So can we think of two numbers that if we take their product, we get positive 100, and if we take their sum, we get negative 20? Well, since their product is positive, we know that they have the same sign. So they're both going to have the same sign. So they're either both going to be positive or they're both going to be negative, since we know that we have a positive product. And since their sum is negative, well, they must both be negative. You can't add up two positive numbers and get a negative. So they both must be negative. So let's think about it a little bit. What negative numbers, when I add when I add them together, I get negative 20. When I multiply, I get 100. Well, you could try to factor 100. You could say, well, negative 2 times negative 50, or negative 4 times negative 25. But the one that might jump out at you is, this is negative 10 times, I'll write it this way, negative 10 times negative 10. And this is negative 10 plus negative 10. So in that case, both our a and our b would be negative 10. And so we can rewrite the left side of this equation as, x, and I'll write it this way at first, x plus negative 10 times x plus negative.
All right, I cannot stand up with this anymore. It's still a guesswork in here. That's not right.
Let's try to find the solutions to this equation right over here. We have the quantity 2x minus 3 squared, and that is equal to 4x minus 6. And I encourage you to pause the video and give it a shot. And I'll give you a little bit of a hint. You could do this in the traditional way of expanding this out, but there might, and then turning it into kind of a classic quadratic form. But there might be a faster or a simpler way to do this if you really pay attention to the structure of both sides of this equation. Well, let's look at this. We have 2x minus 3 squared on the left-hand side. On the right-hand side, we have 4x minus 6. Well, 4x minus 6, that's just 2 times 2x minus 3. Let me be clear there. So this is the same thing as 2x minus 3 squared is equal to 4x minus 6. If I factor out a 2, that's 2 times 2x minus 3. And so this is really interesting. We have something squared is equal to 2 times that something. So if we can solve for the something, let me be very clear here. So the stuff in blue squared is equal to 2 times the stuff in blue. So if we can solve for what the stuff in blue could be equal to, then we could solve for x. And I'll show you that right now. So let's just replace 2x minus 3. We'll do a little bit of a substitution. Let's replace it with p. So let's say that p is equal to 2x minus 3. Well, then this equation simplifies quite nicely. The left-hand side becomes p squared. P squared is equal to 2 times p. Because once again, 2x minus 3 is p. 2 times p. And now we just have to solve for p. And I'll switch to just one color now. So we can write this as, if we subtract 2p from both sides, we can get p squared minus 2p is equal to 0. And we can factor out a p, so we get p times p minus 2 is equal to 0. And we've seen this show multiple times. If I have the product of two things and they equal to 0, at least one of them needs to be equal to 0. So either p is equal to 0 or p minus 2 is equal to 0. Well, if p minus 2 is equal to 0, then that means p is equal to 2. So either p equals 0 or p equals 2. Well, we're not quite done yet because we wanted to solve for x, not for p. But luckily, we know that 2x minus 3 is equal to p. So now we could say either 2x minus 3 is going to be equal to this p value, is going to be equal to 0, or 2x minus 3 is going to be equal to this p value, is going to be equal to 2. And so this is pretty straightforward to solve. Add 3 to both sides. You get 2x is equal to 3. Divide both sides by 2. And we get x is equal to 3/2. Or over here, if we add 3 to both sides, we get 2x is equal to 5. Divide both sides by 2. And you get x is equal to 5/2. So these are the possible solutions. And this is pretty neat. This one right over here, you could almost do this in your head. It was nice and simple. While if you were to expand this out and then subtract this, it would have been a much more...
They should call this one solving the equations by doing structure adding or subtracting.
The quadratic formula.
The quadratic formula. Oh, this video is quite long.
In this video, I'm going to expose you to what is maybe one of at least the top 5 most useful formulas in mathematics. And if you've seen many of my videos, you know that I'm not a big fan of memorizing things, but I will recommend you memorize it with the caveat that you also remember how to prove it, because I don't want you to just remember things and not know where they came from. But with that said, let me show you what I'm talking about. It's the quadratic formula. And as you might guess, it is to solve for the roots or the zeros of quadratic equations. So let's speak in very general terms, then I'll show you some examples. So let's say I have an equation of the form ax squared plus bx plus c is equal to 0. You should recognize this. This is a quadratic equation where a, b, and c are, well, a is the coefficient on the x squared term, or the second degree term. B is the coefficient on the x term. And then c is, you can imagine, the coefficient on the x to the 0 term, or it's the constant term. Now, given that you have a general quadratic equation like this, the quadratic formula tells us that the solutions to this equation are x is equal to negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. And I know it seems crazy and convoluted and hard for you to memorize right now, but as you get a lot more practice, you'll see that it actually is a pretty reasonable formula to stick in your brain someplace. And you might say, gee, this is a wacky formula. Where did it come from? And in the next video, I'm going to show you where it came from. But I want you to just get used to using it first. But it really just came from completing the square on this equation right there. If you complete the square here, you're actually going to get this solution. And that is the quadratic formula right there. So let's apply it to some problems. So let's start off with something that we could have factored, just to verify that it's giving us the same answer. So let's say we have x squared plus 4x minus 21 is equal to 0. So in this situation, a is equal to, let me do that in a different color. In this situation, a is equal to 1, right? The coefficient on the x squared term is 1. b is equal to 4. b is equal to 4, the coefficient on the x term. And then c is equal to negative 21. The constant term. And let's just plug it in the formula. So what do we get? We get x. This tells us that x is going to be equal to negative b. Negative b is negative 4. Negative 4. I put a negative sign in front of that. Negative b plus or minus the square root of b squared. b squared is 16. Right? 4 squared is 16. Minus 4 times a, which is 1, times c, which is negative 21. So we can put a 21 out there, and that negative sign will cancel out just like that with that. Actually, this is the first time we're doing it. Let me not skip too many steps. So negative 21, just so you can see how it fit in. And then all of that over 2 times a. Over 2 times a is 1, so all of that over 2. So what does this simplify? Or hopefully it simplifies. So we get x is equal to negative 4 plus or minus the square root of, see, we have a negative times a negative. That's going to give us a positive. And we have 16 plus, let's see, this is 4 times 1 is 4 times 21 is 84. 16 plus 84 is 100. Oh, that's nice. It's a nice perfect square. All of that over 2. And so this is going to be equal to negative 4 plus or minus 10 over 2. We could just divide both of these terms by 2 right now. So this is equal to Negative 4 divided by 2 is negative 2, plus or minus 10 divided by 2 is 5. So that tells us that x could be equal to negative 2 plus 5, which is 3, or x could be equal to negative 2 minus 5, which is negative 7. So the quadratic formula seems to have given us an answer for this. You can verify just by substituting back in that these do work, or you could even just try to factor.
Alright, now everything just start to make sense again. So indeed, there got some proper formula or standard formula that could be able to solve the answers for the equations. That was nice. So in the end, everything becomes predictable again, which is definitely great. So we don't have to do the guesswork anymore. Let me have a look at this. Strategizing to draw quadratic equations.
In this video, we're going to talk about a few of the pitfalls that someone might encounter while they are trying to solve a quadratic equation like this. Why is it a quadratic equation? Well, it's a quadratic because it has this second degree term right over here, and it's an equation because I have something on both sides of an equal sign. So one strategy that people might try is, well, I have something squared. Why don't I just try to take the square root of both sides? And if you did that, you would get the square root of x squared plus 4x plus 3 is equal to the square root of negative 1. And you immediately see a few problems. Even if this wasn't a negative one here, that's the most obvious problem, but even if this was a positive value here, how do you simplify, or how do you somehow isolate the x over here? You've pretty quickly hit a dead end. So just willy-nilly taking the square root of both sides of a quadratic is not going to be too helpful. So I'll put a big X over there. Another strategy that sometimes people will try to go for is to isolate the x squared first. So you can imagine, let me just rewrite it, x squared plus 4x plus 3 is equal to negative 1. They might say, let's isolate that x squared by subtracting 4x from both sides and subtracting 3 from both sides. And then what happens? On the left-hand side, you do indeed isolate the x squared. And on the right-hand side, you get negative 4x minus 4. And now someone might say, if I take the square root of both sides, I could get, and I'll just write that down, square root of x squared is equal to, and you could try to take the plus or minus of one side to make sure you're hitting the negative roots, negative 4x minus 4. And you could get something like this. You would get x is equal to plus or minus the square root of negative 4x minus 4. But this still doesn't help you. You still don't know what x is, and it's really not clear what to do with this algebraically. So this is yet another dead end. Now, there's some cases in which this strategy would have worked. In fact, it would have worked if you did not have this first degree term, if you did not have this x term, so to speak. Then this strategy would have worked, assuming that there are some solutions. But if you have an x term like this and it doesn't cancel out somehow, if there was another 4x on the other side, then you could subtract 4x from both sides and they would disappear. But if you can't make these things disappear, this strategy that I've just outlined is not going to be a productive one. Now, another strategy that you'll sometimes see people use, especially when they see something like this, let me rewrite it, x squared plus 4x plus 3 is equal to negative 1. They immediately go into factoring mode. They say, hey, wait, I think I might be able to factor this. I can think of two numbers that add up to 4 and whose product is 3, maybe 3 and 1. And then they immediately factor this left-hand expression, say that's going to be x plus 3 times x plus 1, and then that's going to be equal to negative 1. And then they either are about to make a mistake. This is actually algebraically valid, but they either make a mistake or they realize that they're at a dead end. Because just saying that something times something is equal to negative 1 doesn't help you a ton, because it's not clear yet how you would solve for x. Another thing try to do is they'll immediately say, okay, therefore x is equal to negative 3 or x is equal to negative 1, because negative 3 will make this first term 0 and negative 1 or negative 1 would make the second term 0. But remember, this would only be true if you're multiplying two things and you got 0 as their product. Then the solutions would be anything that made either one of those terms equal to 0. But that's not what we're dealing with here. Here we're taking the product is equal to -1. So in order to factor like this and make headway in most cases, you're going to want to have a 0 on the right-hand side over here. And that's also true if you're trying to apply the quadratic formula. A lot of folks would say, okay, I see a quadratic equation right over here. Let me just apply the quadratic formula. They say if I have something of the form ax squared plus bx plus c is equal to 0, the quadratic formula would say that the roots are going to be x is equal to -b plus or minus the square root of b squared minus 4ac, all of that over 2a. And so they'll immediately say, all right, I can recognize a here as just being a 1. There's a 1 coefficient implicitly there. B is 4, c is 3, and then they'll say, okay, x is equal to -4 plus or minus the square root of b squared, which is 16, minus 4 times 1 times 3, all of that over 2 times 1. But there's a problem. The quadratic formula applies when the left-hand side is equal to 0. That's not what we have over here. So we're falling into that same pitfall. So everything I just did, none of this is a good idea. So the way to approach this, if you want 0 over here, you want to add 1 on the right-hand side. And if you want to maintain the equality, you have to add a 1 on the left-hand side. And so you're going to get x squared plus 4x plus 4 is equal to 0. And now you could use a quadratic formula, or you could factor. You might recognize 2 plus 2 is equal to 4. 2 times 2 is equal to 4. So you could say x plus 2 times x plus 2 is equal to 0. And so in this case, you say, all right, x could be equal to -2, or x could be equal to -2. So this one only has one solution. X is equal to -2. But the key is to recognize that you need the 0 on the right-hand side there if you want to use a quadratic formula, or if you want to use factoring in the 0 product property.
All right, that makes sense. So that videos just tell us if we want to use a formula, that formula must have its own conditions. Only if the reality meets that condition, then we could be able to use that formula. Okay, let me do one more thing. Let me just watch one more video.
So we're asked which function has the greater y-intercept. So the y-intercept is the y-coordinate when x is equal to 0. So f of 0, when x is equal to 0, the function is equal to, let's see, f of 0 is going to be equal to 0 minus 0 plus 4 is going to be equal to 4. So this function right over here, it has a y-intercept of 4. So it would intersect the y-axis right over there. While the function that we're comparing it to, g of x, we're looking at its graph, y is equal to g of x. Its y-intercept is right over here at y is equal to 3. So which function has a greater y-intercept? Well, it's going to be f of x. F of x has a greater y-intercept than g of x does. Let's do a few more of these where we're comparing different functions. One of them that's...
This is tedious. I don't think that we need to go through it. Then let's have a look at this one.
Function g can be thought of as a translated or shifted version of f of x is equal to x squared. Write the equation for g of x. Now pause this video and see if you can work this out on your own. All right, so whenever I think about shifting a function, and in this case we're shifting a parabola, I like to look for a distinctive point. And on a parabola, the vertex is going to be our most distinctive point. And if I focus on the vertex of f, it looks like if I shift that to the right by 3, and then if I were to shift that down by 4, at least our vertices would overlap. I would be able to shift the vertex to where the vertex of g is. And it does look, and we'll validate this at least visually in a little bit, so I'm going to go -4 in the vertical direction, that not only would it make the vertices overlap, but it would make the entire curve overlap. So we're going to first shift to the right by 3. And we're going to think about how would we change our equation so it shifts f to the right by 3. And then we're going to shift down by 4. Shift down by 4. Now, some of you...
All right. For this video, we now, again, learned a new word called shift. You know, normally we would like to say move that stuff to a different place. But for now, they use this word shift. Shift to the right, shift to the left, or shift to the up, or shift to the down. Or, yeah, something like that. They use a shift. And let me say, even on our keyboard, there has a key called shift. To be honest, I always do not know what that word means. Why it has to be appear on my keyboard. That makes sense.
You might already be familiar with this, and I go into the intuition in a lot more depth in other videos. But in general, when you shift to the right by some value, in this case we're shifting to the right by 3, you would replace x with x minus 3. So one way to think about this would be y is equal to f of x minus 3. Or y is equal to, instead of it being x squared, you would replace x with x minus 3. So it'd be x minus 3 squared. Now when I first learned this was counterintuitive. I'm shifting to the right by 3. The x-coordinate of my vertex is increasing by 3, but I'm replacing x with x minus 3. Why does this make sense? Well, let's graph the shifted version just to get a little bit more intuition here. And once again, I go into much more depth in other videos here. This is more of a worked example. So this is what the shifted curve is going to look like. Think about the behavior that we want right over here at x equals 3. We want the same value that we used to have when x equals 0. When x equals 0 for the original f, 0 squared was 0. Y equals 0. We still want y equals 0. Well, the way that we can do that is if we are squaring 0. And the way that we're going to square 0 is if we subtract 3 from x. And you can validate that at other points. Think about what happens now when x equals 4. 4 minus 3 is 1 squared. It does indeed equal 1. The same behavior that you used to get at x is equal to 1. So it does look like we have indeed shifted to the right by 3 when we replace x with x minus 3. If you replaced x with x plus 3, it would have had the opposite effect. You would have shifted to the left by 3. And I encourage you to think about why that actually makes sense. So now that we've shifted to the right by 3, the next step is to shift down by 4. And this one is a little bit more intuitive. So let's start with our shifted to the right. So that's y is equal to x minus 3 squared. But now, whatever y value we were getting, we want to get 4 less than that. So when x equals 3, instead of getting y equals 0, we want to get y equals 4 less, or negative 4. When x equals 4, instead of getting 1, we want to get y is equal to negative 3. So whatever y value we were getting, we want to now get 4 less than that. So the shifting in the vertical direction is a little bit more intuitive. If we shift down, we subtract that amount. If we shift up, we add that amount. So this right over here is the equation for g of x. G of x is going to be equal to x minus 3 squared minus 4. And once again, just to review, replacing the x with x minus 3 on f of x, that's what shifted right by 3, and then subtracting the 4, that shifted us down by 4. Shifted down by 4 to give us this next graph. And you can visualize, or you can verify visually, that if you shift each of these points exactly down by 4, we are indeed going to overlap on top of g of x.
Okay, I guess that's today's learning, and I hope you enjoy this. I guess the most important knowledge for you guys in this video or in this lesson is that it is quadratic equations, or sorry, that should be the quadratic formula. It should be, oh, here we go. This one. That's the most important knowledge that you need to know and memorize if you have to take an exam. Okay, that's it. I'll see you guys in the next video. Bye.